welcome back. We're going to go a little bit more in depth into partial pressures. Partial pressures, of course, is the sum of all of the pressures of every gas that's in a mixture of gases. We have Dalton's law of partial pressure down here, and it just says exactly that. The total pressure is equal to the partial pressures of all of the different gases in the sample added up. The partial pressure of a gas happens to be directly proportional to the number of moles of each gas. Okay, so that means that the pressure of an individual gas over the total pressure, this is a ratio right here, is equal to the number of moles of that individual gas over the total number of moles in the sample. Again, that's a ratio. All right, the partial pressures of a gas is directly proportional to the number of moles of the gas. Okay, so that's what this formula right here says. And then, of course, we're going to, as we do this partial pressures section, we're going to have some partial pressure of water vapor, because a lot of times we'll collect a gas over water. We'll bubble gases up through water, and water right at the surface will vaporize. Okay, so if you have some sort of container here, and in that container you have some water, right at the surface of the water you're going to have little molecules of water turning into a gas. Okay, and those little gas molecules will be floating up above the surface of the water. Now, if you have some other gas, let's say maybe we have some sort of a tube here, and that tube is connected to, it's connected to some other, reaction, and in that other reaction a gas is produced, right? So the gas from this other reaction is going to flow into this tube here, and then it's going to bubble up through the water, and then it will collect up here with this water vapor. Alright, so that means that up here above the surface of the water, okay, and let's say that this is like domed off, it's encapsulated so that they can't get out, right? So you have little water molecules in gas form, and you have whatever this other gas is here. Okay, so you have two different things. If you want to calculate the partial pressure of just this purple gas, let's say here, you need to know what the partial pressure of water is. So we have this chart where it tells us at different temperatures what the vapor pressure of the water is. We can use Dalton's law of partial pressure here to subtract the vapor pressure of water and figure out what the total pressure, or what the pressure of the individual gas is, assuming we know what the total pressure in the sample is. Alright, so let's do some practice questions. In order to do a lot of the questions, and both of the ones that I'm going to be showing you today, we need to know what a mole fraction is. Okay, a mole fraction is that ratio that we talked about, okay, on the right hand side of the other equation. So let me just rewrite that equation real quick. Alright, we said that P1 over P total was equal to the moles of that gas over the total moles. Okay, well, this side of the equation is called a mole fraction. Alright, that mole fraction again is the individual moles, okay, over the total number of moles. Alright, so that's what this side is. Okay, so that means that we can say, oh, and mole fraction, by the way, has this little symbol here. This is the Greek letter chi. Alright, C-H-I. Alright, so we can say then that the mole fraction of a specific gas is equal to the number of moles of that gas over the total number of moles in the sample. And also, since this side right here is a mole fraction, that means a mole fraction is also equal to the pressure ratio we talked about. Okay, so we can say then that the mole fraction of a specific gas is equal to the partial pressure of that gas over the total pressure of all of the gases in that sample. Okay, so we actually have two different equations for mole fraction now. Let's use our knowledge to figure out this problem. Equal masses of nitrogen, okay, that ended in gin, that means it's diatomic, so we're going to go ahead and write that formula right there, of nitrogen and argon gas are mixed at 25 degrees Celsius such that the total pressure in the container is 723 torr. What is the partial pressure of the argon in this mixture? Okay, so let's kind of get an idea about how we're going to figure this out. They just said that we have equal masses of nitrogen and argon gas. We have a total pressure, and we have a temperature. Now, from the formulas that we had listed just a moment ago, that the mole fraction is equal to the number of moles of a gas over the total moles of a gas, and that the mole fraction is equal to the partial pressure of a gas over the total pressure of the gas. Okay, we need to be able to plug our information into those formulas. Okay, that means here this temperature, that doesn't fit either of our formulas that we have over here, so we're not going to end up using that temperature at all. Okay, mass. Mass can be turned into moles. Okay, and since they have equal masses, we can just pick whatever we want and use that as the mass for both of them. Alright, so we can solve for the moles of each gas, and I tell you what I'm going to do is I'm going to pick that the amount of grams for each gas, I'm going to choose 39.948 grams because that is the molar mass of argon, which means we'll have 1 mole of argon if we pick that number. Okay, so if we plug in, do a little dimensional analysis here, right? Our grams divided by the molar mass will end up with moles. Okay, so this right here is moles of nitrogen, and here we get moles of argon. Okay, now let's refer to this definition of mole fraction, okay? The moles of the individual gas over the total number of moles. So the total number of moles are these two right here added together. So that's going to give us our total number of moles to be 2.4260. Now we can get the mole fraction of argon by plugging into this formula right here. Okay, we can take the moles of argon, 1, and we can divide it by the total number of moles, and that will give me the mole fraction of argon. Once I have the mole fraction of argon, I can remember that I have this total pressure right here, and I can solve for the partial pressure of argon, right? So the partial pressure of argon, we would have to multiply top and bottom, or excuse me, we would multiply, by the total pressure on both sides of the equal sign, and so that means that the partial pressure of argon is going to be equal to the total pressure of the sample times the mole fraction of argon. And remember, we're getting that mole fraction from this top formula up here, okay? The individual moles of argon divided by the total number of moles in the sample. Alright, so let's calculate that mole fraction of argon. So we do our 1 divided by the 2.4260, and that gives us our mole fraction of argon. This is a unitless number because you have moles on top and moles on bottom, and so the mole variable cancels. So this is a naked number on purpose. It's not supposed to have any units. Okay? Alright, and now we can wrap it up and do this last little part there. Okay? we're going to solve for the individual pressure of argon. This side right here, this is that mole fraction. That's that number right there. Okay, this whole side equals this number. Okay, so let's see what our answer is. Alright, so the partial pressure of argon is going to be the mole fraction times the total pressure. That gives us the individual pressure to be 280 torr. Alright, now the question didn't specify what unit they wanted it in, so we're just going to leave it in the unit that they gave it to us, torr. Okay, let's look at the next question. Alright, nitrogen gas and oxygen gas. Okay, so remember those are both diatomic, right? So nitrogen and oxygen are collected over water. Remember what I told you, if we collect something over water, at the surface of the water, it's going to vaporize. It's going to become a gas at the surface. So we're going to have nitrogen gas, oxygen gas, and water vapor gas all mixed together. Okay, and so this is all happening at 25 degrees Celsius in a 1.5 liter vessel. Use the information in the table to complete the rest of the table and answer with 1 sig fig for everything. Okay, so let's go ahead and get started. I'm noticing I've listed over here to the side a bunch of equations that we might end up using, and I'm noticing that we forgot one we're going to need, and that is the ideal gas law, PV equals nRT. Okay, we'll definitely need that. Okay, so let's get to work. I have the mole fraction for my nitrogen and my oxygen, and I don't have anything else, okay? So if I'm looking at my formula, this mole fraction right here is equal to the moles of nitrogen over the total moles, but I don't know either of those things individually, so I can't solve for the other one, right? I have two unknowns in the equation. I only know this. I don't know either of those. Also, that mole fraction is equal to this, but over here I have two unknowns. I don't know the individual pressure and I don't know the total pressure, so I can't solve for either of those two unknowns. Okay, so I'm going to either need to figure out what the total number of moles is, or I'm going to need to figure out what the total pressure is. And if I can figure out either of those things, then that means I'll be able to figure out the individual number of moles, and I'll be able to figure out that individual partial pressure. Okay, so let's see here. Water. I don't know anything about that, or it seems like I don't know anything. I know that all of this is happening at 25 degrees Celsius. So if I look down in my table of vapor pressures of water at 25 degrees Celsius, I see 23.8 torr. Now you might be tempted to write 23.8 torr right here in the pressure of water, but I'm going to ask you not to do that because we have PV equals nRT over here. And our gas constant R is 0.0821 atmosphere liters per mole Kelvin. Okay, so we really need to be in atmospheres. Alright, so we are going to take then that 23.8 torr to be our given, and 760 torr is equal to 1 atmosphere. And of course this, by the way, this is the partial pressure of water. Okay, so that partial pressure of water then is going to be 0.0313157895 atmospheres. Okay, now the table said answer everything with 1 sig fig, so we're going to put in 0.03 atmospheres here. Okay? Alright, let's keep going. Something else we know is that the mole fraction has to add up to be 1. Okay, all the mole fractions of all of the different gases, they all have to add up to be 1 in our table. Okay, so I'm going to go ahead and put a 1 right here, and that means that this has to be 0.3. Okay, now we are cooking. We know that the mole fraction of water is equal to the individual number of moles over the total number of moles, and it's equal to the individual pressure over the total pressure. Well, we know what the individual pressure of water is, and we now know what the mole fraction of water is. That means we can solve for the total pressure of the entire sample. And if we can do that, then that unlocks nitrogen and oxygen for us. Okay? So let's see if we can rearrange that equation to solve for the total pressure. Alright, so let's see, we've got P total would be equal to, right, so I would multiply by the total pressure on both sides, and then I would need to divide by this mole fraction on both sides. So that means that it's going to be equal to the individual pressure over the mole fraction. Okay? So that's what we're going to do with water. The total pressure of the sample here is going to be the individual pressure of water divided by the mole fraction of water. And you want to use the big long number, not this rounded one, because then that's going to mess up our answer later on, okay? So when we do that division, we end up with 0.1 atmospheres. Okay, that's of course with sig figs. We need to write down the entire answer, okay, the big long number, so that we can use that for our other calculations. So let's see here, let's do that. The total pressure is equal to 0.10438599649 atmospheres. Okay, so now that we've done that, we can figure out what the individual pressures are of the other gases in the sample, okay? And we've actually lucked out here. We have the same mole fraction for water as we do nitrogen, and we know here that that mole fraction is equal to the individual pressure over the total pressure, right? So if we're solving for the individual pressure of a gas, that means you would take the mole fraction times the total pressure, okay? The mole fraction times the total pressure. If you take the mole fraction of 0.3 and multiply it by the total pressure, you're going to get this number right here, okay? It's actually, you'll get this big long number here. That means nitrogen's going to have the exact same number, okay? So we can put 0.03 atmospheres there for nitrogen, okay? Now we have some options, okay? We can go ahead and do the exact same thing and say, 0.4, this mole fraction for oxygen, times the total pressure of the sample, okay, and we'll get a value. Or you can say that this plus this plus this all has to be the total pressure, right? That's Dalton's law of partial pressure right over here. So you could solve for oxygen that way, okay? So since I've already got this number, the total pressure, stored in my calculator, I'm going to go ahead and just multiply that times the 0.4 value and do it that way, because that seems easiest to me right now. So let's see here. That's going to give me 0.04 atmospheres for my partial pressure of oxygen. All right? And if you add up those values there, okay, then you are definitely getting 0.1 atmosphere, so we did that right. Now let's move over to the moles part of this, okay? We know that we have the partial pressures of all of the gases. We have the total pressure of all the gases. That is equal to the mole fraction of all of the gases. We want the individual number of moles. We still, however, have two unknowns, okay? We know this, but we don't know this, okay? We have to know one of these two things here to solve for the other one. Let's try and get the total number of moles of the sample, and we're going to use PV equals nRT to do that, okay? We know that we've got the total pressure. They gave us the volume in the beginning of the problem. They said that it was a 1.5 liter vessel and that this was happening at 25 degrees Celsius, which we will turn into Kelvin, okay? So that's equal to N, and since we're plugging in the information about total pressure, that means that we're going to get total number of moles, okay, so times RT, right, nRT. So I want to know what this total number of moles is, and if I know that, then I can solve for the individual. So I'm going to divide both sides by RT. So the total number of moles then is equal to the total pressure, which we have labeled right here, okay? So it's equal to the total pressure and of course that's in atmospheres, times the volume, 1.5 liters, over the gas constant, times our temperature in Kelvin. Remember, to get the Kelvin temperature, you're going to take whatever the temperature is in Celsius and add 273.15 to it, okay? And that's how we got that value. All right, so let's figure out what our total number of moles is. Okay, so when I do this, I'm coming up with the total number of moles in the sample to be equal to 0.006, that's a 3, let's write that a little bit neater, 966,914. Ooh, that's a lot of numbers, right? But they only want that to 1 sig fig, so that stops right there, okay? So let's put that up in our chart, 0.006 moles. Okay, and now we can go through and we can figure out what the individual number of moles are, okay, because we have the mole fraction for each gas and we have the total number of moles, so we can solve for the individual moles, right? And we would do that by multiplying both sides by the total number of moles, okay? So that means that the individual number of moles is going to be equal to the mole fraction times the total number of moles. Okay, so we'll take that total number of moles that we just found, not the sig fig version, but the full number, and we're going to multiply that by the mole fraction so that we can get our individual number of moles. And again, nitrogen and water have the same mole fraction, which means they're going to have the same individual number of moles. So we can multiply that number by the total number of moles we found and come up with a value here. So let's see, for nitrogen, I'm getting 0.0019, so that's going to be 2, which means water is the same thing because they both have the same mole fraction. Okay, and then we can do the total number of moles times 0.4, and that'll give us our oxygen value. So I'm getting 0.00255. So with one sig fig, that's going to be 3. Right? Now, you probably spotted a problem, okay? 2 plus 3 is 5, plus 2 more is 7, and this is a 6. That doesn't equal. If you added the full decimal number of each of these together, you would get the full decimal number of the total number of moles. But because we've rounded this and done sig fig stuff to it, that's why it's not exactly equaling up there. But rest assured, if you added up their full decimal numbers, you would get the full decimal value for the total number of moles. So we have done everything correctly. It's just our rounding is making it look a little odd there. Okay, so those are two examples of partial pressure questions where you're having to use mole fraction in order to find the answer. I guarantee that this question here, or something very similar to it, will show up on your test. So make sure that you have paid attention to how this problem was solved. Okay, we had to get the mole fraction of water first, then we found the partial pressure of water. Then that allowed us to figure out what the total pressure of the sample was going to be because we had both of these pieces of information, and once we had the total, we were able to get these. Then we used PV equals nRT to get the total moles, and that let us get these. In essence, the key to the problem is finding out the totals for pressure and number of moles. Alright, as always, thank you so much for learning with me today, and I will see you next time.